On July 20th, 1969, Neil Armstrong became the very first man to walk on the moon. This marked the date that humans had ever traveled to a different celestial body. Ever since the dawn of the space program, humans have achieved some amazing things, sending satellites into orbits, the lunar landings, and sending probes past our solar system.
But even though we consider those great achievements, we haven't even scratched the surface when it comes to space travel. Our universe is billions of light years across, yet we haven't even moved 1 light year away. Now, based on this, it's easy to see why we may never travel to other galaxies. Or will we?
Well, how is it possible?
Well, there are a number of solutions that have been proposed that might one day help us reach distant galaxies.
Like what?
Well, we have the Alcubierre drive, quantum entanglement, the ion drive, the EM drive.
What about wormholes?
Yeah, that works too.
What is the Alcubierre drive? Imagine traveling through space without actually moving. Sounds weird, right?
Well, it is. The Alcubierre drive is a method of space travel unlike anything we've ever seen before. It works by manipulating the space around you. Now, more specifically, it contracts the space in front of the spaceship while expanding the space behind the spaceship. Now, this sort of creates a bubble around the ship which pushes it forward.
The Alcubierre drive has the possibility to go faster than the speed of light, but it's powered by negative energy, which is a theoretical concept in itself.
So what are the applications of the Alcubierre drive? Well, using current technology, it would take us millions of years to get to even the closest star system. Now, even if we could travel at the speed of light, which by the way is 300 million meters per second, a spacecraft traveling that fast would take over 4 years to get there. Now, using the Alcubierre drive, we could get there in a matter of weeks.
Well, how is it possible to move faster than the speed of light? Well, as far as we know, we can't. That's okay. This drive doesn't move faster than the speed of light. Space itself does. Space is dynamic. There's no limit to how fast we can move it.
The Alcubierre drive isn't the only solution to our interstellar problem. The resonant cavity thruster, or EM drive, is another way to get throughout space. Now, just like the Alcubierre drive, the EM drive uses an unconventional method in order to produce thrust. The EM drive works by bouncing microwaves at a certain calibrated frequency inside of a resonant chamber. Now, due to the shape of the cavity, the microwaves bounce in such a way that they produce more energy than initially put into the system. Now, it's because of this fact that many scientists argue that the EM drive should not be working at all because it violates the law of conservation of momentum.
Now, it's important to note that the thrust produced by the drive is insignificantly low. EagleWorks, a subdivision of NASA, produced 0.3 to 0.5 newtons of thrust. A team in China also reported they recorded 0.75 newtons of thrust. Modern-day rockets can produce thrust of over 30 million newtons, and even that isn't enough to get us to distant galaxies. Now, although it may seem that the EM drive is primitive, with enough time and research, we may be able to use this technology in the future. The ion drive is a form of electric propulsion that creates thrust by accelerating ions. The ion drive is very promising due to its efficient use of fuel. The way NASA's ion thrusters work is by using a 2-electrode system. An upstream electrode called the screen grid, which is charged highly positive, and the highly negative charged downstream electrode called the acceleration grid. Due to the fact that the ions are generated in a region of high positive and the acceleration grid being the high negative, the ions are attracted towards and are focused out of the discharge chamber, creating thousands of ion jets. The thrust force is created between the upstream ions and the accelerator grid. Ion thrusters are capable of propelling a spacecraft up to 90,000 meters per second. The only offset being that the thrusters would have to stay operating for a long time.
We've looked at technologies that require us to travel through space. But what if we wanted to get there in an instant? Well, this is where quantum entanglement comes in, or as Einstein liked to call it,
spooky action at a distance.
Quantum entanglement is a phenomenon that occurs between two or more linked particles. In each set of entangled particles, each one is dependent on the other. In order to describe how quantum entanglement works, we first have to take a look into quantum mechanics. Similar to the binary language used by your computer, entangled particles can have a physical state of spin up, which would be binary 1, or spin down, binary 0. The difference between binary and entangled particles is that the entangled particles aren't defined until they are observed. This means that each particle is spin up and spin down until we look at it. If one particle in an entangled set is measured to be spin up, then the other particle will be the exact opposite. We can use this principle to our advantage. If we took half the entangled particles and moved them to a location we wanted them to travel to, for example, Mars, we can then analyze the spin of every particle in our body here on Earth. By doing this, the information is sent to the entangled particles on Mars. We would essentially be teleporting there, but by doing so, the version of you here on Earth would be destroyed. Now the problem comes when we want to travel to distant places. If we would like to use quantum entanglement for that, we actually have to travel there first, because we have to send the entangled particles to where we want to be. Even though this concept seems like science fiction, it's actually being proven here on Earth. Anton Zeilinger, a quantum physicist, conducted an experiment where he scanned a single photon and by using two entangled particles was able to send that photon to a distance 80 miles away.
Now let's take a look at possibly the most familiar type of interstellar space travel, wormholes. We've all seen the movie Interstellar and are amazed by how they use the wormholes to travel from galaxy to galaxy. But in order to do that, there's a few things that must first come into play.
When wormholes are first created, they are very unstable and require an external force to stabilize them. Now this may not even be possible because the stabilizing force is negative energy. And as we discussed earlier, negative energy is a theoretical substance.
The way wormholes work is by bending space-time and bringing two distant objects closer to each other. It's almost like having two separate holes on a paper, bending the paper, and then poking a hole through the papers to connect the holes.
Also, when they were first created, scientists predict that wormholes will be so microscopic and would only expand as the universe expands. Now, even if we could create our own wormhole and stabilize it, the moment we try to send something through it, it would instantly collapse. The only way to stabilize it while putting something through it is again with negative energy. Another problem, or solution depending on your point of view, is that when traveling through a wormhole, you may experience time dilation. Now this is the same time dilation you would experience if you were near a big gravitational force, such as a black hole. Now, say for instance, your journey in the wormhole lasted 3 days. That few day period for you may have lasted years for an observer on Earth.
Now we've looked at all the possibilities for interstellar space travel, but the sad truth is, it'll take a very, very long time to actually implement them. A scientist by the name of Andrew Kennedy theorized the weight calculation. It uses the world's global GDP and how fast technology is advancing to predict how long humans will actually start using interstellar space travel. And its prediction is it'll take over 1,000 years.
The weight calculation does not take into consideration the difficulties that we come across in space. Like for example, the billions of asteroids between us and our destination. Now these high-speed collisions with the asteroids have the ability to obliterate our spaceships. So how can we make interstellar travel easier for us? Well, humans aren't the only ones that can travel into space. We have rovers, probes, and robots. Now we can send these machines to do the job for us. Now this makes it easier because these machines won't have the need for food, water, or oxygen.
Also, with these rovers and probes, we wouldn't have to worry about the human casualties or psychological factors that go along with an interstellar space travel mission. Like for example, leaving your family to travel to a distant galaxy in a spaceship that may or may not return home, with the newly researched technology that may or may not work. Now we send these machines into outer space and they collect the data for us. Once we get it back, that's when we prepare a manned mission. But the only problem is, these unmanned missions would take a lot of money.
We'd have to factor in costs such as the artificial intelligence to power the robots, employee wages, and general research and development. Now with such a high risk for failure, it's easy to see why we haven't sent humans into space already. I mean, think about it. Why risk all the money and time on a mission that has virtually no return on investment? It's just not economically responsible.